Okay, so hi everyone, welcome back. This is the continuation of the fourth video of the 10th week when we are discussing exercises that were intended for labs. So far, we have already compared stochastic block models to some selected community detection algorithm, which was in this case InfoMap, and in the following, we would also like to do one exercise regarding the core periphery structure of networks, so division into some dense cores surrounded by some sparse periphery, and in particular, we will be looking at the K-cores decomposition of some real networks. Remember from lectures how a K-core is defined. A K-core is a maximum subset of nodes or maximum subgraph of some network where each node in the K-core connects to at least K other nodes in the same core, K-core. K-cores can be disconnected, so for a particular value of K, we can find multiple parts of the network that would be disconnected, and every node in each of these parts connect to at least K other nodes. And during the lectures, we already mentioned what will be a simple algorithm for detecting a K-core for one particular K. What you do is simply you iterate through all the nodes in a network, and on each step you remove every node whose degree is smaller than K. In that case, that node can obviously not be part of the K-core. And you repeat that process until no such node remains. And afterwards, you're left with some subgraph, and connected components of this subgraph will be different K-cores of your network. And this is basically what the first part of this exercise says. So consider the algorithm for computing network K-cores for a specified K-core. So starting with the original network, we iteratively remove all the nodes with a degree less than K, and when no such node remains, the connected components of the resulting network after the removal are actually the K-cores of this network. And also remember from lectures that K-cores are nested. So imagine that I have already computed all the 3 cores in the network. Now, next I want to go and find the 4 cores. I could again start with the original network, but since every 4 core must necessarily be a subgraph of some 3 core, I can only take the network that consists only of the 3 cores, remove all the nodes that have degrees smaller than 4, and the nodes that remain or connected components of the nodes that remain will actually be 4 cores. So I can do all this in one particular iteration. So assume that we have implemented this simple algorithm, and the code is already also available online, but I'm not going to show it now. Let's say that we have implemented this algorithm, and let's say that we apply them to 4 larger networks that are listed here above. And these are the Junk and Java software dependency networks, a network of WikiLeaf cables or references between WikiLeaks cables, and finally the IMDB actors collaboration network. I have selected these networks as an example, but these are surely not the best networks to show the power of K-cores or the power of the K-core core periphery decomposition of the network. I only selected them because I have some meta information or some labels associated with the nodes. So afterwards, when we will be finding out the nodes in the largest K-core, for instance, or something like that, I can print out their labels and see whether I get some reasonable result. So once again, I only selected these networks because there are some labels associated with the nodes. So let's say that we apply this k-call algorithm to this network, and let's print out for each value of k the number of k-cores for that value of k, and also the size of the largest one. So for each value of k, I will remove the nodes with degree smaller than k, and at the end I will compute the connected components of the resulting network. The number of connected components is the number of k-cores, and I can also look at the size of the largest connected component, which will be the size of the largest k-core. And what we will be also interested, what is the maximum value of k, here which we will denote with k sub max, for which there exists at least one k-core in your network. So imagine that for if we find this k sub max, there are no k-cores of the network where k will be set to something larger than k sub max. So not looking at the code, let's just look at the results. So first here I'm applying this k-core decomposition to the junk software network, and you can see I found 5 one-cores, and the largest one consists of 381 nodes, and the largest k for which I found at least one core is when I set k to 6, so I found a 6 core, and it consists of 11 nodes. If we go on to the next network, the Java dependency network, we can see that the largest k core is the 25 core, and it consists of 43 nodes. Then for the WikiLeaks network, the largest k core is the 11 core, and I actually find 2 such k cores that are not connected between each other, and the largest one consists of 14 nodes. And finally, for the actor collaboration network, the largest k core that I find is 144 core that consists of 162 nodes. Notice that if I found 144 core, the size of it should be at least 145, so that everybody can connect to at least 144 nodes. And I would also like to highlight that there is no reason why the number of k cores for different values of k when you increase k should decrease. So for instance, I found 7 2-cores, then I found, for instance, 2 10-cores, but I get 3 11-cores, and so on, so these values are not necessarily decreasing. So far nothing particularly interesting. All that we found is what will be the value of the largest k, for which we found at least one k-core, and in the handout we have denoted this with k sub max. Now, as a final exercise, let us print out the labels of the nodes in k sub max core and see whether we get something reasonable. This is also the reason why I need to have labels associated with the nodes. So let us first again look at the software graphs. For instance, for junk software dependency network, which is a network analysis library written in Java, which are the classes of this library that are in the largest k-core? Notice that these are visualization classes. So the majority of the classes are in the package junk visualization, while I also get, I believe, 2 classes in the package junk algorithms layout, which are basically algorithms for layouting the nodes in order to prepare visualization. So in the case of junk, we can say that the nodes in the highest, the largest k core for the largest value of k are the values or are the classes for visualization. And this turns out to be a relatively general result. Also, for instance, for Java class dependency network, The largest K core is a 25 core consisting of 43 nodes. And notice here that most of the nodes are in java.avt package, which stands for Abstract Window Toolkit, which is the framework for developing graphical user interfaces in Java next to the Swing framework. There are also some other classes here that are more or less used throughout the entire Java, like the simple class or class object, string, and so on. So in general, if you would study different software networks, you will always realize that the most central, densest part of those networks are different visualization classes that use each other very often. And I'm just showing you here results for two networks, but you can believe me, I have studied a lot of software networks. Always the densest, most central part are visualization classes. Then if we move on to the WikiLeaks network, the largest K cores are 11 cores, and I actually find two. And I'm here printing out the labels or the IDs of these WikiLeaks cables. And you can see that the first are Oro Colombo. Let's just put this into Google and just a second and see what we get. Come on. Just a second. Okay, we can see that this is some WikiLeaks cable, and it comes from which embassy? I hope that we'll be able to see that. Where will this be written? I believe this is Sri Lanka. Yes, as shown here. And you can see that different cables from the same embassy obviously form some dense 11 core. And the second one is from New Delhi, obviously, and again we get some dense connected part of this network, and the nodes, each node references at least 11 other nodes or at least 11 other cables. And you can go online and read the content of these cables. Maybe we will find something interesting. And finally, as our final example for the case of the actor collaboration graph, you can see that we are finding a large number of different cores for different values of K. The largest K core we find is 144 core, and here are the labels of the nodes or the names of the actors that are in this K core. And I believe that these are mostly wrestling actors or different wrestlers. When, if you remember, these were also highlighted by different clustering coefficients, and when we have analyzed this network when we were studying node centrality measures, and I believe that there will also be some pornographic actors here and so on. So once again, you can look at these results in further detail by yourself, and let me highlight again that this might not be the best examples of networks for finding some core periphery division of that network, so that the core will be something very meaningful in practical applications. I have only selected them because I have some labels associated with the nodes. Okay, so this is more or less it what we wanted to do in these labs. So let me finish here and see you in the next video. Thank you for listening.